Hello, everyone, and welcome. Today, we're going to shrink down to the molecular level and explore the hidden forces that, well, basically run our world. We're talking about the invisible attractions that determine why some things are solid, some are liquid, and why they behave the way they do. Let's get right into it.
All right, so think about this for a second. We see this stuff every day, but have you ever really stopped to wonder why it happens? Like, why does ice float? I mean, that's kind of weird, right? Most solids are denser than their liquids, so they sink. And what's the deal with honey? Why is it so thick and gloopy while water just splashes right out of the spoon?
And this image right here shows exactly what I'm talking about. The property we're seeing is something called viscosity, which is just a fancy word for a liquid's resistance to flow. You can see one liquid is thick, slow, almost resisting gravity, while the other just goes for it. This isn't magic, folks, it's chemistry, and it's all about how much the molecules want to stick to each other.
And that's really the big secret. It all boils down to these invisible, you could almost call them sticky forces. These are the attractions that exist between all the individual molecules in a substance, pulling them together and dictating pretty much all of their physical properties.
So, let's actually pull back the curtain on these so-called sticky forces. We're going to dive into what they are, how they work, and really importantly, how they stack up against each other in a kind of hierarchy, from the absolute weakest attraction to the strongest.
Okay, so let's get the official term on the table. We're talking about intermolecular forces. And I need you to lock this in. These are the forces between separate molecules, not the super strong bonds inside a single molecule, like the ones holding the hydrogen and oxygen atoms together in H2O. Now, intermolecular forces are weaker, kind of like the magnetic pull between tiny separate magnets. But don't let weaker fool you. They are the entire reason solids and liquids can even exist.
Now, these forces come in a few key varieties, and we can rank them by their strength. We're going to start at the bottom with the weakest but most universal, which are called dispersion forces. Then we'll level up to dipole-dipole forces. And finally, we'll get to the heavyweight champion of the group, the mighty hydrogen bond.
So let's start at the very bottom of that ladder. We're talking about the most fundamental force of them all. This is the one that exists in every single atom and molecule in the universe, no exceptions.
They're called dispersion forces. So picture the electrons buzzing around a molecule like a cloud. It's random, right? So for just a fraction of a second, you might get more electrons on one side than the other. This creates a tiny, temporary imbalance of charge, a flicker of positivity on one side and negativity on the other. That temporary little magnet can then induce a similar effect in its neighbor, and for a split second, they attract.
Now, how strong these forces are depends on something called polarizability. It's just a word for how easily that electron cloud can get distorted or, squished around. Big molecules with lots of electrons, they have big squishy electron clouds. They're highly polarizable. That means they can form stronger temporary dipoles and have stronger dispersion forces. It's why something like octane, a big molecule, is a liquid at room temperature, while methane, a tiny one, is a gas.
Okay, next step up the ladder, dipole-dipole forces. These happen in molecules that are what we call polar, meaning they have a permanent positive end and a permanent negative end. So unlike the temporary flickering of dispersion forces, these molecules are like a bag full of tiny permanent magnets. The positive end of one is always attracted to the negative end of another. It's a much more consistent and therefore stronger attraction.
And that brings us to the big one, the superstar of intermolecular forces. This is the force that explains so many of water's incredibly unique properties. Let's talk about the hydrogen bond.
So what is a hydrogen bond? You can think of it as a dipole-dipole force that's been hitting the gym. It's an incredibly strong version that only happens under a very specific condition, when a hydrogen atom is directly bonded to one of three very greedy elements, nitrogen, oxygen, or fluorine. Just remember, hydrogen is having FON, FON. And you'll know when to look for it.
Okay, let's connect the dots. We've got our first big mystery. Why does ice float? We know water is H2O. That means it has hydrogen bonded to oxygen. So it's the perfect candidate for hydrogen bonding. How does this super strong force make solid water lighter than liquid water?
And here is the beautiful answer. As water freezes, those powerful hydrogen bonds grab hold and lock the water molecules into this rigid crystal lattice. And look at that structure. It's an open hexagonal shape. And the key word there is open. See all that empty space in between the molecules? That's wasted space. When ice melts, that rigid structure collapses, and the molecules can tumble around and pack in much, much closer together. So, all that empty space makes ice less dense than liquid water, and that's it. That's why it floats.
All right, we've cracked the case of the floating ice. Now let's use what we've learned to tackle our other questions, starting with that super slow pouring honey. And this brings us right back to that idea of viscosity. The rule of thumb is really simple. The stronger the intermolecular forces, the more the molecules cling to each other. And the more they cling together, the harder it is for them to move and flow past one another, which means you get a higher viscosity.
So let's do a head-to-head comparison. Water's got those strong hydrogen bonds, right? But honey is made of these big, long, complex sugar molecules. So not only do they have very strong dispersion forces because of their size, but they're also absolutely covered in places where they can hydrogen bond. So you've got this double whammy of forces that causes the molecules to get all tangled up, making it really difficult for them to flow. And that's why honey has that incredibly high viscosity.
Okay, so we've seen how these forces hold things together, but what does it take to break them apart? What happens when we introduce a new player into the game? Energy, specifically in the form of heat.
Think about melting a piece of ice. When you add heat, you're just pumping energy into those water molecules. They start to vibrate and shake faster and faster. Eventually, they're vibrating so violently that the energy of their movement becomes stronger than the hydrogen bonds holding them in that fixed crystal lattice. The bonds break, the structure collapses, and voila! The solid melts into a liquid where the molecules are finally free to slide around.
And this quote really just sums it all up perfectly. At its core, the difference between a solid, a liquid, and a gas is just a constant tug of war. It's the energy of the molecules trying to fly apart versus the strength of those sticky intermolecular forces trying to hold them all together. It's that simple, but it's also that profound.
So the next time you drop an ice cube in your drink or you watch raindrops speed up on a leaf, you'll know exactly what's going on. It's all about these tiny yet incredibly powerful invisible forces. So I'll leave you with this question. What else in your daily life is being secretly shaped by these forces? Once you start looking for them, you'll realize they are absolutely everywhere. Thanks so much for joining me today.